Struggling with math? You're in the right place. Welcome to Explaining Mathematics, the channel where we simplify tough problems, break down complex formulas, and turn confusion into clarity. From basics to advanced topics, we explain it all step by step. Let's start solving.
All right, today we are jumping into one of the most, elegant and powerful tools in all of math, the quadratic function. Now, this is a concept that shapes the world all around us in ways you probably don't even realize, and we're going to break it all down. So let's get right into it. So this is what it looks like in its standard form. It might seem like just a jumble of letters and numbers, right? But it's actually a super powerful piece of mathematical code. This one little line can describe the arc of a basketball shot, it can help engineers build the perfect satellite dish, and it can even model the rise and fall of business profits. So what is this formula really telling us? How do we get from these symbols to a shape that actually describes things in the real world? Let's dive in and find out. To really get the whole picture, we first have to understand the parts. Every single piece of this formula, the variables, the coefficients, even that little exponent, it all has a specific job to do. Once we get their roles, the whole thing just clicks into place. First up, we've got x, our variable. This is the input. It's the part of the function that we can change. Think of it like a recipe. X is the ingredient you can adjust to see how the final dish turns out. It's the number that isn't fixed. Next, you've got a, b, and c. These are the coefficients. Now, unlike x, these numbers are fixed for any given function. They are like the tuning dials on a machine. Each one tweaks the final outcome in a very specific way, shaping and positioning the result of our little formula. And then there's this tiny 2. Honestly, this is the heart of the whole thing. This little exponent has one simple instruction: multiply x by itself. And that one simple move is what gives the function all of its unique properties and its famous curved shape. It's the whole reason we call it quadratic. It comes from the Latin word for square. Okay, so we've decoded the parts, right? We have a variable we can change, we've got coefficients that act like our tuning dials, and we have that squared term giving it all its power. So what happens when we plot all the possible results on a graph? You get this perfect symmetrical U shape called a parabola. This is the visual signature of every single quadratic function. All those numbers and symbols, they all work together to create this one single elegant curve. This shows you just how much those tuning dials matter. Remember a, the first coefficient? Well, it's pretty much the master control. If a is a positive number, the parabola opens up, kind of like a smile. But if a is negative, it flips completely and opens downwards, like a frown. It's such a simple switch, but it has a huge visual impact. The other coefficients handle the fine-tuning. That a value, it also controls how wide or narrow the curve is. Then the b value, working together with a, shifts the whole parabola left or right. And c is the easiest of all. It literally just tells you where the parabola crosses that vertical y-axis. With these 3 numbers, you can place and shape this curve anywhere you want. Okay, so we understand the shape. Now let's get practical. One of the most common things we want to know is, where does this curve land? If it's the path of a ball, where does it hit the ground? This is absolutely crucial for stuff like physics and engineering. Answering this question is really the key to unlocking the function's predictive power. We have this beautiful curve, sure, but we need to find specific, meaningful points on it. Where does our function's output actually hit 0? The answer to that question has a name. They're called the roots or zeros of the function. These are just the specific input values, the x's, that make the entire function equal 0. And if you're looking at the graph, they're the exact spots where the parabola crosses that horizontal x-axis. So, how in the world do we find these roots? Well, we use a very special tool, the quadratic formula. Now, I know it can look a little intimidating, but it's basically a master key. You just plug in your a, b, and c from any quadratic function, and this formula will spit out the exact roots. It unlocks the solutions for literally any parabola you can think of. So we've gone from the formula to its individual parts, to its shape, and even to its solutions. Now let's bring this all back to the real world and see just how fundamental this curve really is. This one function is the backbone of so many different fields. In physics, it's used to model the path of pretty much any object thrown through the air. Engineering relies on that parabola shape to design everything from suspension bridges to satellite dishes. Financial models can use it to find maximum profit. Even computer graphics artists use it to render smooth, realistic-looking curves. And that kind of brings us full circle, doesn't it? This quote really nails the core idea. The algebra in the formula, the parabola on the graph, and the roots that we solve for, they aren't separate things. They are three sides of the very same story, each one describing the exact same powerful relationship in a different language. And that's really the final thought to leave you with. We've seen how a few symbols on a page can predict the path of a ball and shape the technology we use every single day. It kind of makes you wonder, if this is what just one function can do, what other mathematical codes are out there, quietly describing our world, just waiting for us to find them?
If this video helped you understand the topic better, don't forget to like, subscribe, and turn on notifications so you never miss a lesson. Comment below what topic you want explained next. Thank you for watching Explaining Mathematics. See you in the next problem.